All right, so have any of you ever gotten lost while you're trying to cross the street? Chances are the answer to this question for most of you is no. Unfortunately, this frustrating experience has been expressed by some of our clients. Without a visual point of reference, it is nearly impossible to walk a straight line over a distance, even as short as a crosswalk. Good evening, my name is Chris, and I am a fourth-year electrical engineering student.
My name is Matthew, and I am a computer engineering student.
I'm Samuel Morris, and I am a mechanical engineering student.
And I'm Megan Leach. I'm an electrical engineering student here, and together we make up Line of Sight. And our hope is to create a device that will help people who are blind navigate the city in a safer manner.
Tonight, we would like to take some time to go over the need that we identified for assisted straight line navigation. We are going to cover the process that we used to develop a solution, our technical design, and we will demonstrate our prototype.
So one of the clients that we got a chance to work with has been blind for 25 years. He's experienced in navigating the city with both his white cane and his guide dog. One day he had to drop off his guide dog at the groomers and walk back home only using his white cane. He stepped off the bus that he had taken, attempted to cross the street, and veered to the left. He never made it to the other side of the sidewalk and, frustrated, had to turn around, go back to the sidewalk he started, find it, and then attempt this whole process again. He eventually made it to the other side, but a walk that should have only taken him 10 minutes to get home wound up taking an hour.
This frustration has also been documented in a research that was conducted at the Max Planck Institute in Germany. This study discovered that a person who has no visual point of reference will walk in circles with a diameter of 20 meters or less. We then conducted further interviews and more research, and we found out that a person who is blind has a hard time walking in a straight line when there are no physical indicators for them to follow, such as a curb with their white cane. So this is the problem statement that we chose, and we started to build a solution targeted towards this problem.
The primary function of any device that solves this problem is that it must guide someone who is blind in a straight line when they want to be guided. So there are multiple secondary functions required to fulfill this primary need. So first, the device must receive some sort of input from the user, which then signals that the course should begin tracking. Along the course, it must detect course deviation, and then it processes some inputs from the environment and produces course-correcting information. All of these secondary functions work together to fulfill that primary need. We've scoped our product down to Canadians who are blind. We've done this because Canada poses some interesting environmental challenges, which if you've been outside today, you've experienced. And I'll talk about that in just a second. We've also limited our target users to be those who are 16 years and older and independent city navigators, because we want our product to be an assistive tool, but it's not something that someone should depend on. Finally, we've limited our situation to walking across a street, because navigating a crosswalk is a situation where straight line navigation and safety are both of very high importance. Like I said, our product must operate in Canadian weather conditions. We've also decided that our product must be drop resistant and must keep one hand free to coincide with traditional use of a white cane. Our product must have 1 degree of resolution and plus or minus 1 degree of accuracy so that the feedback being received by the user is accurate and safe enough. Finally, the product has to be able to be used independently by someone who is blind. So that means our product cannot have visual aspects such as a display that needs to be read.
For this project, we decided that a good solution to the problem would have a certain set of characteristics. One of those characteristics was a low cost to the client. Some of our clients don't have extra money to be spending on expensive new electronics. Tied to this is a long life expectancy so that the product didn't have to be replaced often. We also wanted the product to be easy to put on, take off, or pick up and start using. And then to get the functions actually up and running, we wanted that to be as quick as possible. We also wanted a short response time and a high update rate so that the product was safe for the clients to use. Lastly, we wanted ease of implementation, which means that we wanted as few devices as possible to actually implement this solution.
With these objectives in mind, we began developing possible solution alternatives. We came up with a large variety of options that we could potentially use. We then began filtering them down to identify the best one. We started by looking at our functions and constraints to ensure that whatever solution we did pick would be able to meet these requirements. We then used a variety of other techniques, and our final decision was based off of a weighted decision matrix. This is the final decision that we moved forward with.
The design we pursued is called the Accumulated Linear Bearing Assistive Handle, or the ALBA handle. First, this device is very easy to use. With just a single button, the user can control their navigation in a straight line. Second, the system is completely isolated, which means it doesn't rely on external factors or infrastructure being installed where it's being used. You can use it anywhere. Finally, the system is very responsive, so the time between receiving inputs from the environment and producing outputs for the user is almost immediate. So what we've actually designed is we've redesigned the handle for the white cane to add additional functionality that helps guide someone in a straight line. Some of our clients expressed concern about a battery-powered solution because they don't want it to give up on them and leave them stranded. Fortunately, our design is simply an extension of the white cane, and if at any point you maybe forget to charge your cane the night before, you simply go back to using traditional white cane techniques.
Our prototype was divided into 3 main subsystems. We have our hardware system, our software system, and our mechanical enclosure. Our hardware system consists of a battery charging circuit and a lithium-ion battery. This was used to power our Arduino Teensy, which is a microcontroller. This microcontroller is connected to our inertial measurement unit, which gives us data from the gyroscope, which tells us the angular velocity of the cane. This information is then processed by our software.
The first thing that the software does is, after it powers on, it sends 3 pulsing vibrations to the handle, which will be simulated through the use of a speaker in the demonstration. These 3 pulses notify the user that the system is on and ready to start tracking, so that someone does not begin walking out into the street not knowing that the device is not really on. Next, the software goes into a main loop. The first thing that it does is read an angular velocity from a gyroscope, and the velocity is integrated to accumulate angular deviation. As soon as that deviation falls outside of some safe range, the user is alerted by another buzz. That loop continues over and over again in quick succession, safely guiding someone in a straight line.
The physical handle here, the physical handle is a part of the cane that contains all the electronic components that are required to guide the user, and they all have to fit in there. And we designed it with very specific requirements. First, like it had to accommodate the placement of like the electronics in the proper locations, and also it had to accommodate the proper placement, like the proper orientation of some electronic components, such as the inertial measurement unit, which had to have its z-axis in a certain orientation, which is perpendicular to the plane of the handle. And the enclosure also needed to be strong enough for daily use and stable enough and durable for day-to-day use. And its dimensions had to be very similar. It had to closely resemble the dimensions of the original handle, so that the user can use it without feeling like something strange, like so that they're used to it, and without feeling the difference, really. And some of the challenges that we encountered with this design is that the handle is too long for the 3D printer. How we produce it is that we printed it in a 3D printer, and we had to split it into various pieces so that they could fit actually in the 3D printer. And this gave us another challenge, is the connection of the different pieces together. So we chose metal bolts and nuts to fit the pieces together, and we had to tighten them so that the whole thing is stable and strong and durable for the users. And another challenge also is that the 3D printed plastic is not quite as strong as other materials or plastics, so we just increased the thickness to accommodate for that.
So our solution is based on a technique that our clients already know how to use called shorelining. If somebody is walking down a sidewalk, the idea behind shorelining is that they can use something like the grass beside them or the edge of the sidewalk as a tactile reference point so that they know that they're still walking on a straight path. The way that our device uses this is the user would step up to the sidewalk, they would step off the sidewalk and square themselves up so that they know that they're lined up with the other side of the street. This is also a technique that our clients use regularly. Then they would turn the device on. So you'll hear the 3 beeps to know that it's working. And then this sets your reference point to straight across the street, and it sets up what we call virtual walls that you'll be able to shoreline between. So now the client can start to walk and shoreline between these virtual walls. And each time that a virtual wall is hit, you can see that it beeps. If this allows the users to know that they are walking at a straight trajectory and hitting those walls at regular intervals. So if the user wound up turning into one direction, the cane would start to beep and wouldn't stop beeping until they align themselves to their previous orientation. So the idea is that both the left and right sides of the cane are supposed to vibrate. So if the left side of the cane is vibrating, you're supposed to correct away from that vibration. Moving forward, there are a few adjustments we'd like to make to this design. One of them is to replace the Teensy Arduino with an MSP430 microchip. The Arduino was quick and simple to implement into this project, but the MSP430 is smaller, more cost-effective, and uses less power. It can still do all the computations we need it to. Another thing we'd like to do is add functionality by adding an adjustable safe zone. So this could adjust the width of the corridor that the users have to suit their needs and preferences. Another function we'd like to add is horizontal tracking. So it works similar to how the angular tracking works. It's just that once the user left their safe zone, the handle would give them feedback to get them back to where they need to be in that safe zone.
When we started developing the Alba handle, the first thing that we did was sit down with the potential users and have discussions. From those discussions, we devised a set of functions, and then we built a prototype that satisfied those functions. So the most important step moving forward is testing our device with the clients and getting practical feedback, finding room for improvement. So a success analysis will include actually getting the product into a user's hands and finding its practical use as a navigational tool. Thank you everyone for your time tonight, and we would love to take any of your questions.
Questions from the floor?
How can you be sure that your client has put the cane directly in front of them so that their range is actually straight? Or is it like
So got to make sure that they're lining up with the correct orientation to get them across the crosswalk straight, basically. I think Megan can answer that one.
Sure.
Yeah.
So that's a skill that they're actually trained in already. So one thing that the CNIB does for their clients is they actually help them with city navigation. So one of the techniques that they're already used to using is when they step off the curb, they use that side of the curb to line their heels to so that they can make sure they're facing in a straight direction. So all we're adding is that they have to hold a cane in front of them. So that's already a technique that they are trained in.
Just curious how fast your air with your integration of the angular velocity builds up. Like, do you end up getting deviation of your virtual walls, or can you comment on how you would correct that?
So we did wind up getting a little bit of an issue with that right now because we don't have a good way to correct for it like in real time, like no sort of averaging software or anything like that. Basically, we'll calibrate the device before we use it. So, and then we'll manually add like a DC offset to our device, and basically that with that DC offset, you can walk really like for a really long ways without that without your virtual walls actually starting to skew away from where they originally were. So in the future, we'd probably also implement some sort of averaging software that would adjust that that offset as you used it.
Yep.
Could the user recover from a fall, or does that destroy the dead reckoning?
That sort of thing would probably destroy the dead reckoning because it it's based on that initial kind of lineup that they had to begin with. So, yeah. Sean?
This is your prototype. Would there be any major changes, say, to the handle in terms of the different suggestions you had for the final product in terms of the innards, but also maybe changing some stuff in terms of the handle if you're looking at sort of an ultimate final design? Any comments or thoughts about that?
Right. What we would really like to see is all of those electrical components shrunk down. Like I mentioned, using the MSP 430, and we have the IMU is on a breakout board right now. So if we took that chip off the breakout board and put it onto a custom PCB, then we'd be able to drastically reduce the size of a lot of this stuff. So if we could actually fit that inside the canes that they already have, or sorry, the handles that they already have, basically. So we'd just be cutting that handle open, putting our electronics inside, and then probably a few extra holes for buttons, and that would really be it. And just make sure everything's nice and watertight, shockproof. Mano?
Yeah, I don't have a background in electronic components, but I was wondering, so you guys said that Berkeley doesn't allow, you guys don't have an ability to go side to side, just perfectly side to side, which is fair enough.
Yeah.
But does it also, does it have an ability to account for twisting? Like, it doesn't matter which orientation you start with, or does that play any role in it?
We believe it would play a role in it, and we haven't accounted for it in our prototype, but we decided that if we stuck the IMU on a bearing, like on the inside of a bearing somehow, and weighted the bottom of that bearing, that way you could twist the cane in any direction, and the weight would keep the IMU lined up with the axis that you expect it to be in. So.
And maybe one more.
At the back?
Oh.
Sorry.
Can this device be put into like any kind of cane, or like is it designated to one specific cane?
Matt will field this question.
So what we've done with the prototype that we have today is we've actually taken the top segment of the cane with the handle, and we've untied the bungee that's inside the handle, and we've taken the top segment off. And we have constructed a new piece which replaces that top segment. So all that the installation requires is that the bungee is fed back up through the new section, and then the rest of the cane still fits into that new handle.
Maybe one last.
Can the blind person go back to where they came from? Would help with that?
Well, they would have to.
They'd have to
Yeah, in order to do that, they would have to get to the other side of the sidewalk and then,
redo it again.
yeah, reline themselves up so that they could have that straight bearing to begin with. So.
All right, thank you very much, Lance.